innovation, coalescence, and resilience. Without materials, there is no engineering. Good afternoon, my dear friends. Well, uh, I would like to concentrate on the theme of this particular meet that you have evolved over the past so many days. What does it say? It says innovation, coalescence, and resilience. Okay, given my expertise, I will try to show how this coalescence can lead to innovation and resilience. Okay, frankly speaking, I may be taking you a bit into your technical terms where you have all studied over the past few years in your college. Okay, so now let me tell you, my topic is going to be something like without materials, there is no engineering. Do you agree or no? Yes or no, please. Or maybe you can raise your hands if you can. Fine, that's good. I think I find some people. So that makes my life more easier right now. Fine. Okay. So now let me come back to what we are trying to say about materials and how it is related to your engineering. Fine. Now, let us first get back to some other properties that you might have been doing in your laboratories at your college. There are many number of properties. I think to name a few, mechanical properties, physical properties, chemical properties, electrical properties, corrosion, biological. So now, materials have their own properties, just as we people, like I have my own properties, I have my own preferences. So that's the same way the materials. Now, where does engineering come in? You need to have a particular material for a particular application. That is where the materials play an important role. Now, with this particular background, let me get back into some more technical terminology where you all might have heard about stress and strain. In fact, this morning also, we could hear what is known as stress and strain. The same thing applies to our human life also. Fine. Okay, now you all must have measured your stress and strain diagram in your laboratories. What does it reveal? It reveals about the strength, isn't it? This strength of the material is essential when you are designing any material. And mechanical engineers are meant for design. But then, when you design a component, you design it for a certain life period. Let us say an engineering component in an industry is designed for 25 years or maybe 25,000 hours. Fine. So what happens after the 25 years of service life or maybe after 25,000 years of running life? So we have to again recheck, recalibrate the whole thing and then see. So this is where again the properties play an important role. Now, if you are talking about properties in your laboratories, you might have measured it in different specimens. Then you extract a specimen always from a working component. So there are ways and means of doing it, what is known as non-destructively. I hope everybody understands what is meant by destructive. And non-destructively, I do not really disturb the design of the component. I just go with my probes. I hope everybody understands what is meant by probes. Like when you go to a doctor, he first checks your temperature and some of the vitals, and then he puts a stethoscope on your chest or whatever. What is he trying to do? That's a probe. He's trying to probe your chest or heartbeat. Similarly, there are umpty number of probes. Now, in this context, I am reminded of one particular quote by the famous scientist Galileo. I hope you all must have heard his name. Galileo said, measure every property that can be measured or otherwise make it measurable if it is not being measured so far. Fine. So that is the philosophy when we are trying to go to an industry and we try to investigate or try to understand the properties in a non-destructive way. This particular way, we have been able to monitor the life after certain service life. Okay, so now this is an equipment where a lot of capital investment has gone into it. So definitely, I don't think anybody would like to discard it for whatever reasons. Okay, it can be environmental reasons, it can be financial reasons in the sense that huge costs are involved in again making such things. So you would like to run it and go ahead with the particular thing. So if you find these particular properties matching with the original virgin materials, we can use it for certain more time with certain precautions. And maybe we can suggest like we go for an intermediate check at particular intervals. Maybe if it is a 25-hour cycle, we say that you go for a check after 3 years or 4 years. Similarly, if it is a 25,000 hours cycle, we ask them to go for a check after 5,000 hours or 6,000 hours. So this is the way that collaboration in the sense that you are having an engineering component and you are all design engineers, you have equipment which is working, you have to keep it going, but then there is a capital investment cost involved, there are environmental issues in disposing these things. So how do we go about? So we try to measure these properties. So it is at this point that I say we have to collaborate. So collaborate in the sense we have to understand what are the properties that are necessary for the operation of this particular machinery or equipment, and then try to measure those properties. As Galileo said, one particular example which I think again I go back to my stress strain diagram, saying that basically it all tells us about the Young's modulus. Young's modulus is also obtained from your stress strain diagram, which also tells us about the strength. Okay, so further if I want, I can give you one more example. None of the pure metals are used in any components. It is only alloyed. This comes, I don't think, this comes very easily for an engineer, but others can take care of it. So do collaborate and form a team and make a resilient system so that it can survive the next few years with whatever precautions that you have told them and regular monitoring. So this is how I would say that in a real life, whether it is on a shop floor or in our own body, we can say that collaboration is necessary for a resilient life after a particular service conditions. So, and that is what is known as innovation in the sense that you're not going to throw away all these things. Yes, now there are methods of recycling, but then for recycling also you need certain inputs, fine. But before we recycle, the life has to go on. So for this reason, we will say that innovation occurs only when we are able to run the present equipment or machine or even my own self for some more time. In the meantime, the backroom boys can plan for particular new innovations and all these things. So to say that, I would say that collaboration or coalescence leads to innovation which should survive the resilience. So this is in a broad way how I would like to correlate all these things. To tell you a few examples, a turbine. A turbine is a high temperature component working under severe conditions. Okay, but then it has its own life. Okay, so that life, after it is expanded, it cannot be thrown away. Okay, so what should we do with it? We make what is known as a remaining life estimation. Okay, and then we try to see whether it can run for few more times or it has to be replaced. So that is what I call it as repair if there is any problem, refurbish it if there is required, if small replacements can be done, and then run it. So these are the three things that are dependent on whatever I call as collaboration, for innovation and resilience. Okay, so please, my dear friends, try to understand that this is what we do in a real life on a shop floor or something like that. Okay, but then when I come back to our own human life, you see these days, these multi-speciality hospitals have come up. What do? They prescribe a number of tests. Okay, and finally, when the report comes, the doctor makes a final decision. So, it's not only one doctor, but it's a collaboration of a whole gamut of doctors with different specializations that has collaborated and given up this particular output, which is making life expectancy growing more and more. Now, this is how I relate it with a daily life or a human life. Further, now take these 5 fingers in our hand. Okay, each one has a different name, different function also. And if one of them is not functioning, I am sure you will have difficulty in carrying out your regular day-to-day activities. For example, I can say that, in somewhere I think we all know that Sri Krishna tried to lift a mountain with his little finger. It's called little finger. But if that is hurt or that is not working properly to your expectations, just try to imagine how we will have your food, which is something like the fuel to our body. So this is how I think coalescence or collaboration leads to resilient systems, and that is how the innovation works. We cannot just simply throw away. Thank you.